Hello, I just wanted to finish where we left off in class the other day. I can't remember if we finished part A and part B or just part A. So I'm going to start part B just in case. So we're applying the chain rule. And again, anytime we have something in here that is not just a plain old x, we have to use the chain rule. So that is the case right now. So again, chain rule says we take the derivative of the outer function, preserve the inner function, and then take the derivative of the inner function. So in this case, y prime is going to be the derivative of the outer function, which is negative sine. Again, preserve the inner function right there, and then take the derivative of that. All right, so the derivative of x minus 1 is just 1, and so that is our derivative right here. All right, and then finally we've got y prime here, again, outer function, inner function, because that's not just an x. All right, so derivative of the outer function tangent is secant squared. We leave the inner function alone, and then we take the derivative of the inner function. So the derivative of 3x is 3. And again, just to tidy things up a little bit, we usually move things like that to the front. So we would get y prime equals 3 secant squared 3x. Okay, these parentheses are optional, but I just put them in. Okay, so then let's take a look at ones down at the bottom here. Sorry, my desk is a little crowded. Okay, so again, I'm looking at what we're taking cosine of. It's not just an x, so we do need to use chain rule. Okay, so then I go and I take y prime. Derivative of the outer function is negative sine. I leave the inner function alone, and then I take the derivative of the inner function. So that would be times 6x. And again, I'm going to move this to the front just so it doesn't get confused with what I'm taking sine of. And so to do that, we would end up with y prime equals negative 6x sine of 3x squared. And again, you can put parentheses around that 3x squared like I did here, but you technically don't need it, so you could just leave that. Okay, this one is a little bit tricky because, again, you might think, well, here's an x squared, that's not just a 3, that's not just an x, so I need to use chain rule. But again, look at this. Clearly this is by itself, right? So we're talking about this as being separate from that. And then we're saying, well, that's cosine of 3. Well, cosine of 3 is just a constant. 3 is a constant, so we're taking cosine of 3. Again, that could be like pi over 6 or 30 degrees or something. That is a number. So actually this is the coefficient of that x squared. Right? So if I were to take the derivative of this, again, think of this if it were just 3x squared. I would just use the power rule here. It's just that this coefficient is kind of weird looking, but I would still just use this as the coefficient and then just use straight power rule for that second part, right? So y prime, so the derivative of x squared, well, let me just write the coefficient down, that scalar, right? And then the derivative of x squared would just be 2 times x. And then again, I would bring that 2 up front, and so we end up with y prime equals 2 cosine 3x. All right. Okay, next one. Now this is different right here. The parentheses indicate that this right here, again, it looks so much like the previous one, but the parentheses tell us that this is what we're taking cosine of. Right, so it's not just a constant like this or a coefficient, a scalar. It's actually cosine of this. All right, so we do have to use the chain rule. So cosine is the outer function, and then this is the inner function. All right, so derivative of cosine is negative sine. Preserve the inner function, so 3x squared. Now I have to take the derivative of this. All right, so there's 2 ways you could handle this. One is you could say, well, what is 3x squared? Well, that would just be the same as 9x squared. So you might want to just take the derivative of that, which would be 18x. Or you could say, well, the derivative of 3x squared, I could use the chain rule, which would say bring the 2 down to the front, leave the inner function alone, and decrease the power by 1, and then take the derivative of the inside, which would be 3. Sorry, that's getting kind of squished. Either way, I end up with 18x. 3 times 3 is 9, times 2 is 18. All right, so instead of writing that over again, I'm just going to use this since I did it on the side. So then the derivative of this would be 18x. Right, and again, our work to justify it is over on the side. We've done that before in class where we take the derivative and just leave it over here. Okay, so then I'm going to bring that 18x out front. So I end up with y prime equals negative 18x sine 3x quantity squared. Okay, for part D, this one's a little bit different. Each time here we've just had cosine of something, and that had an x squared, cosine of something. Now we have cosine of x, but it's actually cosine x and then squared. And what happens now is cosine becomes the inner function and squared becomes the outer function. Right, when we just had cosine of something, cosine was the outer, but now that we've got that squared, again, that's another way we can rewrite it, that becomes the inner function and squared is the outer. Right, so then to take the derivative of that, we get y prime equals, take the derivative of the outer, so that's the power rule. We're going to bring the 2 down to the front, leave the inner function alone, decrease that power by 1, I'm not going to write it, it would just be a 1, and then times the derivative of the inner function. And the derivative of the inner function here is negative sine x. All right, so we end up with y prime equals negative 2 sine x cosine x. And we're just going to leave it like that. This is the 2 sine x cosine x is a trig identity, but let's just leave it like that. Okay, and then this last one, again, if we rewrite this, this is y equals cosine x raised to the 1/2 power. So again, we see that now cosine is the inner function and square root, or the 1/2 exponent, is the outer function. Right, we take the derivative, y prime, bring the 1/2 down, leave the inner function alone, decrease the power by 1, so this becomes the negative 1/2, and then it says take the derivative of the inside, which is negative sine x. Right, I'm just going to clean that up a little bit, so then we end up with y prime. The 2 is going to be in the denominator. The cosine x, the 1/2, is going to flip down to the denominator. So the only thing that's in the numerator is negative sine x. And then we've either got cosine 2 cosine x to the 1/2, or if we want to write it the way that they gave it to us, let's change that to negative sine x times 2, over 2 square root of cosine x. Okay, next page. This is where things get a little bit dicey, right? Because if you take a look at this, right, so it's saying it's a repeated application of the chain rule. We are going to actually have to do this 3 times. Let me rewrite it. So this is f of t is sine cubed of 4t. So I'm going to rewrite this as sine of 4t to the 3rd power. Right? So we have the cubed as the outer function. And then this is a little bit different from the one that was like that we did part D right here, because we still had an outer function like that, but the inner function was just a straight up cosine x. That x inside meant we could just take the derivative of cosine as negative sine x. We didn't need to use the chain rule there. But again, this part right here is saying, oh no, actually, we do need to use the chain rule for the inside part, because this is not just a plain old t, and so we're going to also have to include the derivative of that, right? So it just makes things a little bit more complicated here. So what we're going to do is we're going to first take the derivative of the outer function. We'll leave this alone. Then we're going to take the derivative of the inner function. Maybe we want to take the derivative of that on the side here. So let's say that this is g of t, our inner function. All right, so if g of t is sine 4t, then when we take g prime of t, we take the derivative of the outer function, which would be cosine, preserve the inner function, which is 4t, and then we would multiply it by the derivative of the inner function. All right, so that would end up being 4 cosine 4t. All right, so when we get to this part where we're ready to take the derivative of the inside, remember that we've done it over here on the side. All right, so when we go to take f prime of t, the whole function there, we take the derivative of the outer function, which is bring down the 3, leave the inner function alone, which is sine 4t, decrease the power by 1, so we get 2, and then we have to take the derivative of the inner function. And again, we just did that on the side, so this would be times 4 cosine 4t. And again, you don't have to do it on the side, but just remember that this is going to have 3 parts to it. The outer, the cube, the inner, the sine, and like the inner, that 4t. Okay, let's clean up. So then we end up with f prime of t equals, I'm going to collect these things out front here. So this is a 12. And then I'm just going to bring the cosine up front just because it's not squared. So we'll have cosine 4t. And then you could either write this part as is, but I'm going to put the squared back where it was between the sine and the 4t. Right, and that would be our derivative. Okay, last one. Right, this one's a bit of a doozy, so hang on. Okay, so find an equation of the tangent line to the graph of f of x equals 2 sine x plus cosine 2x at the point pi 1 as shown in figure 2.26. Let me just sketch that for you just so that you can see what it looks like, but you can look in your book to see it. Right, so we've got pi over 2, pi, 3 pi over 2, and 2 pi. And then at 0, it's 1. And then, again, I'm gonna maybe butcher this a little bit. I'm gonna try to draw it as accurately as possible. So then at 3 pi over 2, it's down here at 3. And then it crosses over about here. And it does a little dip here. So it's going to come up like this. And then it's going to go up, let's say, maybe like 1.5, a little bit higher than that. It's going to dip down in here in the center and come back up. And then it's going to dip down here. And it's going to go down. Oops, my pencil's hitting the stand. All right, and then it's going to go up like this. Actually, and then it's going to turn around, sorry. It's going to kind of hit at 1 and go down. Again, that some of these parts might not be entirely accurate, but it looks like that roughly. And so it's asking us to find the equation of the tangent line at that point pi 1. And so we're looking for something maybe that looks like that. All right, again, figure 2.26 in your textbook will give a better, more accurate drawing than what I have right there. Okay, so again, if you remember from what we did before, finding the equation of a tangent line, we need 2 things. We need the slope at the point, so we need f prime of pi, right? So the slope of the tangent line at pi. And we also need an ordered pair. So this is the slope, and then we need the ordered pair pi comma 1. And we need the equation y minus y1 equals m times x minus x1. All right, so we've got the point, we've got the form here. So really what we're doing right now is trying to find the slope of this function, or slope of the tangent line at pi. All right, so that means we need to find the derivative. So f prime of x, all right? So again, this is in the section on chain rule, so we're assuming that at some point we're going to have to use the chain rule. It's not going to be here because again, we're just taking sine of x, so we're going to use regular trig derivatives here. But this, because that's something other than x, we're going to have to take the chain rule when we get to that, or use the chain rule when we get to that. Okay, so the derivative of this first term, again, the derivative of sine is cosine, so this part is just going to end up being 2 cosine x. But then the derivative of the second part, derivative of cosine is negative sine, so minus sine. We preserve the inner function, which is 2x, and then we take the derivative of the inner. All right, so we've got f prime of x. I'll just tidy up a bit here. I'm going to bring that 2 out front, so we get 2 cosine x minus 2 sine 2x. And then it's, again, we're asked to find the derivative at pi, so we're going to put pi in here. And we get 2 cosine of pi minus 2 sine 2 pi. All right. Cosine of pi is negative 1, so this is going to give us 2 times negative 1. Sine of 2 pi is 0, so this is going to be minus 2 times 0. All right, so then the slope of the tangent line at the point pi 1 is equal to negative 2. Okay, so then we are going to plug it in here. Y minus y1 equals m times x minus x1. All right, so our x1, y1 is pi and 1, so we've got y minus 1 equals m, which is negative 2, times x minus pi. All right, I'm going to just get this in y equals mx plus b form, so negative 2x plus 2 pi. Add the 1 over, so we get y equals negative 2x plus 2 pi plus 1. And that would be the equation that we would use. Again, if we were to do this in the book, it would probably say to move everything over to one side and set it equal to 0, or to put it in standard form, which would mean just move the x over, but I'm cool with that one. Okay, the other part of this is determine all the values of x in the interval 0 to 2 pi at which the graph of f has a horizontal tangent line. All right, so hopefully we can tell that it should be right about here, right? Because again, that would be a horizontal tangent line here, here, and here, and this is beyond 2 pi, so that would not fall in there. All right, so how do we find the where the tangent line would be horizontal? Hopefully you're saying, oh, I remember, that's when the derivative is equal to 0, right? Because again, derivative means what is this? It's the function that provides us the slope of the tangent line, and so we would start out with this. 2 cosine x minus 2 sine 2x, and we would want to set that equal to 0. Okay, this kind of is a bummer right here. If this were just maybe a sine of x, not a 2x, we would handle this a little bit differently, but we're going to use a trig identity for that that says that sine of 2x, sine of 2x is 2 sine x cosine x. And again, those show up in our textbook, so you could just go back and find that. All right, so this ends up being 2 cosine x minus 4 sine x cosine x equals 0. All right, well, I see that I have a 2 in each term, and I see that I have a cosine x in each term. So I'm going to factor that out. So 2 cosine x. And what's left here is 1 minus 2 sine x. And we want that to equal 0. Right, so what we've done is we've kind of spawned two equations right here. We want to know when 2 cosine x equals 0, actually just when is cosine x equals 0. And then the other part is when is 1 minus 2 sine x equal to 0? All right. Well, think about in 0 to 2 pi open. All right. Where is cosine equal to 0? Well, it's whenever the x coordinate is 0 on the unit circle. And so that would be at pi over 2 and 3 pi over 2. Okay, well then let's look at this. This is asking when is sine of x equal to 1/2. All right, so it's positive, which means it has to be in the first or second quadrant. And sine is equal to 1/2 when we're talking about radians that are in the pi over 6 family. All right, so in the first quadrant, that would be x equals pi over 6. And in the second quadrant, that would be 5 pi over 6. All right, Sarah, there are 4 locations where there is a horizontal tangent line. Pi over 2, that's this one right here. And then 3 pi over 2, that's that. And then here pi over 6 would be this one right here, and 5 pi over 6 would be this one right here. Sorry, I'm not sure if you could see that. Pi over 6, 5 pi over 6, these 2 spots right here. Okay? All right, thanks for watching.